Hey folks, welcome back. Sorry for the breaking this into two pieces. We're back to where we are again. I'm going to take off just where we started last. Why is this not working? There we are. Okay. Sorry about that. So welcome back. The plan is to then continue on with our case studies on diffusion and agent-based models. So the models we just talked about, simulation of networks and simulation on networks. And then the question is, can we do both? Well, yes, it turns out, of course. And many times this is really interesting. It's surprisingly less common than you might think, at least for sort of individual investigator kind of simulations. There are some really big social contact simulations for things like COVID and other kinds of diseases, which are based on people moving around cities. But for explicitly network-based simulations, most of them tend to be simulations where it is of and on, but there's no feedback process. And so that's what I'm going to describe to you. This is a piece that we have done before. Myself and Giovanna Murley, Josh Mendelson, and Robin Gutierrez worked on this project. And this is a case where we combined the two elements, but they really were separate. So there was no feedback process in the temporal elements of how this piece worked. So what we did, the question was, in this context, was whether or not the sexual network structure in China, in Shanghai in particular, as that was a case study we were dealing with, was sufficiently dense for or sufficiently structured to allow any kind of a heterosexual HIV epidemic to carry forward. And so on our little rubric of realism versus toy theory versus data, this is very much a data-based realistic aiming model. And so our goal was to literally do a what if scenario kind of thing to imagine what would the likelihood be of an outbreak of HIV in Shanghai if, given what we know about the structure of sexual networks in this setting. And so the way this worked is we ended up having a whole set of networks that we simulated from a known survey of general population workers and commercial sex workers. And we then combined those to create a network. And to do that, we used our exogenous features of the network. That's how we end up constructing the network that underlies the diffusion simulation. And so again, this was a case where we took a sampled bit of data, generated a large scale network, not full scale. It was like, I don't remember the exact size. I thought it was about 10,000 nodes. And then asked what would happen if we had spread equal to that size. And so what is the exogenous features we added? Here's some examples. So we had an age mixing distribution and an education mixing distribution. And so these are heat maps. So we tend to see that people have sex with people who are similar to them in age and similar to them in education. And it differs whether or not you're male or female, and whether or not you mix exactly like you or a little bit older, a little bit longer. We also then had the degree distribution. So for each person, we know their number of sexual partners that they've reported in the past for both women and for men, and a classic sort of age graded longer tail here that you would expect, and a difference in their overall level of education. The one bit that's a little bit wrinkle on this is that we had to add some commercial sex workers to the population, and the number of commercial sex workers you add, we varied that. That was a parameter, but the commercial sex workers differ, of course, from the random people in the population in the sense that their degree distribution of number of sexual partners is much heavier and has just many more partners, of course, than their general population compatriots might. So once it was built, we used a random mixing model. So it was just a version, which is called the zipper method, where it's a really nice, fast way to simulate a network with a known set of exogenous features. And that allowed us then to quickly put together the network but randomize it within the constraints that were constructed on this network. So it's not really an agent rule simulation for constructing the network, but it is a randomized and a simulated version for doing that. The network distribution of component sizes, and this is really the answer to the simulation sort of almost by itself, is that the vast majority of the overall population is not connected, right? So the overall size proportion of the network that is in the largest component tends to be really small, right? There's most of the components are just tiny little isolates over there. And that's because most people in this network have either one partner, right? That's the mode for most people. And particularly for women, and that ends up being the governing feature. So if you have only one or two partners over the course of your set, then it ends up being that most people are in isolated dyads. But the largest connected components are not trivial because this is a big city, right? So even though we only end up with about 15 to 16% of the population in the largest connected component, depending on which draw from the simulation we run, it's still going to be lots of people because Shanghai is such a big city, right? So then we want to ask, well, given that, what's the likelihood that a disease would transmit across this network? Well, for that to happen, what we need to do is ask, well, what does this largest connected component look like? And the largest connected component really depends on our hubs. And so the hubs are generally commercial sex workers. And so you see a node like this that is up in the, multiple tens of partners. And so you end up with a network that has a very strong disassortative mixing pattern, because what happens is commercial sex workers have Johns who then see other commercial sex workers. And so those Johns might have other sets of partners, but by and large, it creates this one or two step hops between commercial sex workers, which then creates the heart, the core of the largest connected component. What then happens from a simulation standpoint? So then this becomes a simulation on a simulated network. And so the way we did this is we used a set of parameters that are about how often people have sex on average, and then the biologically informed dyadic transmission probability given that they have sex. So this is the proportion. So these are the 9, this is the state space. So we have 3 levels of our transmission parameter, 3 levels of our frequency parameter, and then the likelihood that a person transmits a bug between an infected to a susceptible is the joint probability that, the joint probability of that happening given that we've had sex this often at this transmission risk. And so it's a nice, pretty simple sort of simulation from that standpoint, because all the parameters, and if you look under the hood here, I've included a bunch of hidden slides that will talk you through the exact parameters we did. But we really tried hard to identify parameters that were informed by biology. So given what we know about the one-off contact probability of transmission for HIV, and we differentiated men passing to women and women passing to men and the whole 9 yards, we were able to really try to say, like, is there anything we can say about the size of the overall spread of the population? And so it ends up being a case that that even within this kind of a network, right, given the size of the number of times people come into contact and the low dyadic probability of transmission, you end up with really small proportions of people that are ever transmitted, to the disease. So less than 0.2 of 1%. So you end up, like, even in the worst case over here, it ends up being a really small likelihood that you're going to get transmission overhead. So I think it's a nice example. We think it's, I'm biased, I wrote the paper, right? But we think it's a nice example of how you can take a little bit of good quality information, and that's the beauty of the surveys that were done that generated this, and build on that by a few clearly simplifying assumptions to generate then an overall network that then lets you ask what a diffusion process on that network would look like. Now, there's lots of other things you could do to this that we haven't done, right? So there are no neighborhood effects. There are no this is a 2-sex model, which is clearly wrong in this context, right? And so there are lots of things that this model doesn't have, and we also don't remove people once they get HIV. All right, so you can imagine that if in a constant testing regime, that people who get HIV would do something different, right? So there's lots of things that you could do that we haven't done. But again, I think as a prediction model, based on these elements of the piece that gives you a sense of that the risk at least is not particularly high. All right, so hopefully, again, I'm sorry for the interruption between the two parts of this video, but hopefully that gives you a sense of what's happening and the way these models are set up. I want to spend just a little bit of time talking about some pragmatic implementation points. And the implementation points here are generated around some ideas that have to do with really with scalability and where to start. The thinking here is that you're just getting started with these kinds of models. Where do you get your feet wet? If you know nothing about programming otherwise, and you're not fully wedded to R or Python or some other programming language that you've already invested plenty of time in, but you still want to see what it's like to play with a simulation, I really recommend the NetLogo routine. NetLogo is a great place for these kinds of toy models that we've been talking about initially. So you can build models that have really simple rule structures, and a lot of the environment features and run features and things like this, so the global parameter features, they've made those choices for you in smart ways. And so Yuri Walensky is the author of this program, and the sample models they have for you to build from are built by really smart people in a lot of different settings. They literally have hundreds of models you can play with. So it's a very nice way to get started in thinking about agent-based models. If you want to use NetLogo to do a database simulation, you can do that. It just requires a lot more sort of back behind the scenes work to make that happen, to get those things up and running. But again, this is one of the best programs for doing dedicated agent-based models, particularly of these sort of toy varieties where you're trying to learn something about a social process and implement it in a setting. Otherwise, I recommend just picking any program that you're comfortable working in a lot. And that's the real key, is that you really need to understand how your program of choice works. You can write a simulation in Excel if you want to. I don't particularly recommend it, but if you really know how to use Excel well, I'm sure you could do it. But every program that you decide to work with to generate an agent-based model is going to have idiosyncrasies that make it better and faster at some things than it is at others. And so a couple of things that I wanted to highlight that I think are going to be really true for most programs anyway. There might be some exceptions, but by and large, you really want to pay attention to some of these common pitfalls in your implementation of the project. So the first one is to really make sure you understand the data structures you're working with when you design from the ground up, when you design the survey. Right, so what are the data elements you need to update in place? Which do you add to a list? Which do you store for later, right? As you're going through doing a survey or a simulation, excuse me, there are lots of times when you want to save the state space of the model out to review later. So that's to tell you how many people are infected or how many people have recovered or something like this. And so keep in mind very carefully what you're going to do with the simulation, because it might be that you need to store the entire state space, everything about it, because you're going to want to drill down and look at the details here and there. But it might be that you only need to do that for one or two illustrative runs after you've already done a much bigger sort of survey of the state space, where all you care about is the end result. It'll be much more efficient to not save that each time and only come back and do that later, right? So think very carefully about what pieces of data you need to get out of the simulation before you start storing and building these huge data arrays. Similarly, some kinds of data elements are really easy to update, but very difficult to append and change. And so if it's the case that you have a model where your actors have no, what's the phrase, they have no memory, then updating in place is probably the much more efficient way to behave. But if you need your actors to be able to look back in time and remember something they did multiple iterations in the past, then you need to add that to a list in a way so that those prior activities are knowable. So you have to build that into your model. So again, it's just a matter of being clear with the program you use, how you store those data, and only keeping the data you need. Another element that is often easy to forget is to think about something like the order of operations and how those order of operations interact with your data structures. Much of the logic that I've been talking about up until now has been describing things in terms of iterations. And so you might imagine that you would write your code as a loop to go over iterations. So it'd be something like if you have, 50 actors that have a probability of learning something, you could flip a coin, for each of them, and you would do that from, actors equals 1 to 50. And so that loop might look something like this if you're doing it in R. But it turns out, of course, that doing a loop in R is actually kind of a pain in the butt. R, it's not what R is best at, but you could do the exact same thing if you vectorized it and did it here instead, right? And so these two pieces of code will present the exact same thing, but the second will be much more efficient. And this is just a silly example. There are many, many instances where this kind of thing will happen. So oftentimes when I write these programs, I write them in the world's worst way because I'm just trying to think it through. I actually use the programming as a way of helping me think. If you're doing that, your code's going to suck, right? It's not going to be the most efficient code, but you might help yourself figure out what you want to do. It's worth it almost always to go back and then optimize the code and figure out how often you do something that's unnecessary. All right. Another example, these are from Nicholas, a graduate student, Nicholas Rosato Oko here at Duke. Nico is a graduate student who's been doing a lot of simulation models here, and he's really spent a lot of time thinking about some of these things. Keep in mind the size of the project you're working on, right? So if you're working with a population where people can die and be born or come and go, it's much less efficient to recreate a data set that's going to change the number of rows and columns than it might be instead to do something like this, where you build a big data set that then many parts of it will be empty, but then you're coming and going to it and you're not doing that kind of merging process over and over again. Similarly, there are ways in which you can use particular packages that let you loop through the state space of your model in ways that you might not otherwise. So for example, you can, this is another case where Nico gives us, where the map2 function in PER and R will let you go through and look at combinations of arguments in ways that's much more efficient than a do loop over both set. Okay. This kind of thinking doesn't come by sitting down and just writing the model off the top of your head. What you really want to do if you want to have an optimized simulation code is build the model slowly. I build models like onions or ogres, if you're a fan of Disney cartoons, in layers from the inside out, right? And so you imagine what the really active primitive is of your model. So if it's something like a disease transmission model, the primitive element is a transmission from I to J. So I transmits to J if one's infected and the other's susceptible. That element is going to get repeated over and over again. Another then is a primitive element will be an update process. So build these sort of primitive elements first, these functions that then get nested inside of the other functions that you're going to do. And the reason you do this is so that you can just double check the bejesus out of each of these elements and make sure that they do what they're supposed to do. So something like a transmission element, like that element is a micro piece of the model. You want to make sure that if you think the transmission probability is, whatever it might be, that when that element is called 1,000 times or 1,000,000 times, it generates what the binomial theorem tells you that it should generate, right? So double check your work. It seems a silly, stupid thing to do, but you'd be amazed how easy it is to pass arguments in silly ways or make mistakes that you don't appreciate until it's much too late. In part, of course, because when you're writing your own software, which is what you're doing here, you're not going to get a syntax error in a lot of kind of substantive mistakes. The machine will keep running, but it might run in ways that you don't want it to. So that's why you really want to start with the primitives and build out to the more complex set. Well, I don't know what happened there. I lost my spot. The other thing you want to do, and this is going to seem a little stupid at first blush, but you really want to make sure, especially once you get the primitives built and you got it out and you have some iterations going, if that's the way your model's set up, that you do something that lets you know the machine is running. So you want to have it build and send out real-time progress checks. And this is because a simulation model, something like that model we ran on Shanghai, will run for weeks, right? So it's not, you're not going to be able to sit down and just watch this. And the problem with a program that runs for weeks is that if your server went down, or if the queuing got messed up on your VM or something, you're going to end up, and the machine fails, you might not know it, and you might not know how it fails. And so if you can have something that is sending to a log or sending to a log file or something, so that you can open that and look at it and make sure that the thing's still doing what you think it's doing, that's a good thing. This is another point to write out, that if you have a simulation model that's going to run over a whole set of conditions, make sure that you save the result of each condition to some kind of a permanent data set as it goes, so that if it's interrupted in the middle, you don't have to start over at the 111 cell of a 4-layer do loop. You can pick up where it crashed and start over again and append your results, as opposed to have to wait to the end. And that seems like a stupid thing to say, but if you're storing all your results in an in-memory data frame that then gets wiped out when your machine crashes because the instance didn't get saved, you're going to be disappointed, right? So just try to make sure that doesn't happen. Anytime you engage in a simulation process where the thing you're simulating is part of the control parameters that drive the simulation's progress, make sure that you build in some kind of a safety check to make sure that you don't get stuck in an infinite loop, right? Again, lessons learned from hard experience. It's really easy to write code that you would say do while something happens, or do until something happens, but then that while conditions or that until condition never happens. And this can happen, you might think, well, that couldn't possibly be the case. Stupid things like your machine not knowing, if you have an equality condition, but you have a little floating point error in a math operation, so that instead of what you thought was an integer ends up being a real number with a really small decimal out there at the end, then it turns out that the if condition never gets met and the thing never converges, right? And you're sitting there waiting for it to happen and you don't know that it's hung up. That's the example of bad code. So what I now do almost always is I calculate ahead of time, what the maximum number of operations might be, double that, and then put some kind of a primitive counter. Every time it goes through this set, it's going to click off that counter. When that happens, and if it ever gets beyond this place that it's supposed to, it kicks it out and says, there's something wrong here. You've passed your while condition, right? Or write things with inequalities as opposed to equalities, right? So instead of saying do until x equals 100, say do while x is less than 100, right? And so, or less than 101. And so this is the kind of thing that, again, seems trivial when you say it out loud, but you'd be surprised how easy it is to write the code as you're going, just thinking off the top of your head as you're trying to work out elements, and put in these features that will, at the end of the day, trip you up. So really just be forewarned. It's easy to do that kind of stuff. With that being said, your code is your data. And so you need to make sure you build your code and your actual production runs in ways that are auditable and replicable. And this can range from everything from adding in really clear seed values when you're doing random number seeds, to making sure that you comment the bejesus out of the code. So you want to make sure that everything is there so that other people can use them. This is particularly true if you're running a model where you can't control it from soup to nuts, right? When you have to inherit a bit of code, or you have to hand a bit of code to someone else, make sure you practice just good software engineering sort of rules. And the problem, of course, is that none of us are software engineers. We're scientists and we care about the substance, and we're using the software tool in order to create a set of projects. And so it's really easy for us to write bad code because we're not trained how to write code. So what that means is spend a little bit of time helping yourself learn how to code if you're going to do anything beyond some pretty simple models. Because and in an ideal world, you would work with a team and a teammate who can help overlook your code. And so if you have someone who can do a code audit for you, who can look at it and make sure that the code is working the way you expect it to, that's really helpful. At a bare minimum, spend a good deal of time forcing yourself to test your code at the corners, right? So make sure that, if you set the model in a way that that is silly, it gives you a known silly result. You wouldn't maybe plan to do that, but that's what you want to do to make sure the model is behaving the way that it's supposed to behave. Okay, so those are the downsides of things that can go wrong. This is, I still think, a remarkably promising way to do social science. It's growing rapidly. There's a lot of work in agent-based simulation models. Network data are still hard to come by. Network data directly relevant to health, like sexual transmission networks, are even still harder to come by. And then having multiple instances of those where you could imagine playing different worlds is almost impossible, right? So simulation is something that's going to be with us as long as we're doing this kind of work. And our ability to create these fake social worlds that are nonetheless theoretically informative is really kind of fun, and it's really cool. And I think once you get yourself hooked into this, you'll be able to learn that there's lots of things you can do to test your assumptions about the way the world works, and you learn things about way. And so it's really exciting. It can also be incredibly profitable for real world actors. If we want to help the world become more attuned to the ways in which networks can be used to manipulate and help population health, then generating realistic agent-based models based on real data is one of those frontiers that are going to make that useful. And well done, clear models can actually create tools that practitioners can use without having to know how the models were developed, if the models are validated and such as best you can. So we hope to talk to you on Friday about these models. If you have questions or comments, please send them to us ahead of time, and we look forward to talking to you then. Have a great afternoon.